Today I think we will talk about the bonding, okay, and the crystallinity. The chapter 3 is related about the bonding, and we will talk about the crystallinity in chapter 4. Okay? I have elaborated a little bit about the questions. The questions in this chapter. So the interaction between the chains are very important in this chapter. Okay? Interactions such as the chain-chain interaction or the substituent group-group interactions are very important. And that influences a lot to the polymer properties. So let's talk about the chain interactions. So what kind of chain interactions, or what kind of bonds that you know? So bond, okay. And so we need to talk about the primary bond. Primary bond. We have single bond, double bond, triple bond, such as those bonds between the carbon and carbon atom or carbon and oxygen atom is very important, right? That's that forms the backbone of your polymer chain, right? If you're talking about a single bond, then the carbon-carbon interaction is based on the covalent bond. So if you talk about the covalent bond, the carbon has sp3 hybridized orbital structure. So sp3 orbital of the carbon and another sp3 orbital of the carbon will form the covalent bonds. Okay? If you're talking about the double bonds, then the sp2 hybridized carbon and carbon interaction will form the double bonds. And sp hybridization will form the triple bonds and so on. So single bond, double bond, or triple bonds are based on the covalent bonding between the carbon and carbon and oxygen, or carbon and hydrogen, and stuff like that. Okay? So primary bond is very strong. But what about the secondary bond? What kind of secondary bond that do you know? Van der Waals force, Van der Waals bonding is important, yes. What else? Hydrogen bonding, yes, hydrogen bonding is important too. What else do you know? We just talked about hydrogen bonding, right? Ion-ion interaction or dipole-dipole interaction. So I think we can talk about the 4 important aspects of the secondary bonding. Okay? So in this chapter, we'll talk about the chain interactions. Okay? Does hydrogen bonding influences your polymer structure or polymer property? Perhaps. So somebody have knocked on that. So we'll talk about this bonding in the polymers in this chapter. Okay. As we have just talked about, previously, we have primary bonding, such as a covalent bond. We have hydrogen bonding between the hydrogen and the partially positive bond. This is not D, but delta plus and delta minus, where you have a rich in electrons. So the electronegative atom will provide the partial charge to electron deficient hydrogen. So this is a dotted structure rather than solid line structures. The solid line represents your covalent bond, whereas dotted line is partial charge, partial bonding, which is a secondary bonding, right? So hydrogen bonding is one of the important aspects in the secondary bonding. And dipole-dipole interactions are the ones that you have rich in electrons in nitrogen, where you have one unshared electron pair, okay? And you have a triple bonds, and you have rich in electrons, which will provide a partial charge, partial negative charge to the carbon. So this nitrile group and another nitrile group will form dipole-dipole interactions. That's why your acrylonitrile, which has a CN bond in the side chain and another CN bond in the carbon-carbon interactions, will form a very strong dipole-dipole interactions. Okay, and later on, acrylonitrile can be used as a semi-crystalline polymer. That's why we can spin the fiber. That's why you are making, fabrics, clothings out of this semi-crystalline acrylic fibers. Okay? If it's not crystalline and if it's totally amorphous, it will be a rubbery polymer. It's not very strong, so that your fiber will be very much stretchable, just like a 쫄바지. Okay? And if you do not have any crystallinity, and if it's amorphous, such as urethane, okay, then it's much stretchable. Okay? So crystallinity will hold the polymer chain, okay, with those hydrogen bonding, such as the dipole interactions in the case of polyacrylonitrile, to become much more rigid and regular and densely packed, to become a little bit more crystalline than the polyurethane cases. We have ionic bonds, ion-ion interactions, if it includes the metal ions, okay, in your polymeric chains. We have talked about the acrylic acid. Acrylic acid has a structure. In the side chain, you have a carboxylic acid. Okay? Acrylic, such as polyacrylic acid, has a very much water-absorbable structure. So it could be used as a water-absorbing polymer, okay? Such as the polyacrylic acid can be used as a diaper, main components of the diaper, but if you add metals in your polyacrylic acid, you can form ion-ion interactions, okay? And this ion could sometimes be used as a cross-linking agent, okay? Because of the ion-ionic bond interactions. Anyway, the primary bond is the covalent bond, whereas the three of them is called the secondary bond. Okay? So bond strength is quite different between the primary bond and the secondary bonds. So in the next slide, I think I have elaborated a little bit about the strength of the interchain interactions. So primary bonding force, such as a covalent bond, has a bond strength at around 400 kilojoule per mole. Okay? You can calculate this to kilocalorie, but anyway, if it's in the kilojoule, it's about 400. The secondary bonding forces range from ionic bonding to the dispersion. It's coming from the covalent bond to the dispersive forces. Among the secondary bonding forces, ionic or hydrogen bonding force is the highest or strongest, whereas the dispersive force or the dipole-dipole interaction is less stronger than the hydrogen bonding. So if you have a hydrogen bonding forces in your polymeric structure, you have added bonding forces to this covalent bond. Okay? Your bonding force is quite strong in the backbone, but if you have a hydrogen bonding in your side chain, it will be much more stronger. And in the secondary bonding forces, the relative magnitude of secondary bonding force is that if you have ionic bonding, it's much stronger. Okay? I didn't put the number here, but anyway, the relative magnitude is that if we count dispersive force as one, dipole has about 10-fold, hydrogen bonding has around 100 times larger or stronger than the dispersive force. And ionic bond is much stronger. Okay? Anyway, you can imagine how strong the material will be, or polymer will be, if you have secondary bonding forces. Okay? So we will talk about the some cases in next slides about the hydrogen bonding forces. Well, the van der Waals force, let me talk about the van der Waals force. This is the dispersive force anyway, okay? And the van der Waals force is the force between the attractive force and the repulsion forces, between your molecules or atoms. If you think about the carbon and carbon interactions, okay, it starts from your atom, carbon and carbon will get closer and closer, and you have some points where some points in your distance where the potential energy is the minimum. That's the distance where your bond between the carbon and hydrogen or carbon and carbon may have interactions. Okay? If you force a little bit more and a little bit closer, then you have repulsive forces, right? Repulsive forces, so your potential energy will increase. And this distance here is the optimum distance between the atom and atoms. This is what we call the Lennard-Jones potential, okay? Potential energy. I think you have already done in your physical chemistry or general chemistry courses. And therefore, the attractive force increases if you at this distance, at this bond distance, your attraction and the repulsion is balanced, okay? Whereas repulsion increases if you pack a little bit more, closer, okay? And vice versa. Anyway, the permanent dipole, another permanent dipole interaction, or induced dipole interaction will influence these van der Waals forces. So this is what we call the dispersive force, or the van der Waals dispersive forces. The hydrogen bonding is the one that this is one of the strongest secondary bonding forces, where hydrogen atom is attached to these electronegative atoms, okay, such as oxygen and hydrogen, okay, or carbon and the oxygens, carbonyl. And this case is the carboxylic acid. If you have two carboxylic acid, okay, carboxylic acid, we have a hydrogen which has two unshared electron pair, so it's rich in electrons, whereas neighboring hydrogen will be, the bonding through this hydrogen bonding. So we put this in a, not the solid line but the dotted line, and you have about few tenths, maybe 40 kilojoule per mole, compared with 400. So it's about 10 times less bonding forces for this hydrogen bonding than the covalent bonding. But if you have this type of hydrogen bonding, then you have very strong interactions between the oxygen and hydrogen in your neighboring groups. Okay. So in this case is carbonic acids or carboxylic acid cases. Another example is about the amide, polyamide. Okay, polyamide has a carbonyl, of course. So you have a two unshared electron pair. You have an amine group, of course. Amine has a one unshared electron pair, but the hydrogen in this amine group will interact with the carbonyl, so you form this hydrogen bonding, okay, between the amide, carbonyl, and the amine groups. And this is the case of amide. So if you think about the polycarboxylic acid or polyamide, you have a very strong hydrogen bonding. Okay? And another example is hydroxide cases. If you have a OH group, okay, OH group, such as the case of polyvinyl alcohol, and the another ether group will form the hydrogen bonding as well. But in this case, you have a one hydrogen bonding, whereas this is a two hydrogen bonding and so on. So polycarboxylic acid or polyamide will have a hydrogen bonding, and this hydrogen bonding can be detected by infrared spectroscopy. Okay? If you look at the infrared spectroscopy, carbonyl peak appeared usually, if it's an ester group, if it's COO ester group, it appears at around 17, 15. If it's ketone, if it's 17, 15. But if it's in ester, it appears at 1735 reciprocal centimeter. But if it's carboxylic acid, it comes down to the downward, so it appears at the lower frequency level, which is around 1680, because of the hydrogen bonding. Right? If you have hydrogen bonding, the IL, the spectrum is moving toward the lower frequency region. So carboxylic acid, if you do not have any the hydrogen bonding, carbonyl appears around maybe 1710 or 1720. But if your carbonyl appears 1680, yes, you can find that this should have hydrogen bonding and so on. So if you have hydrogen bonding, always your frequency will move to the lower frequency level. Same as the amide group as well. If it's ketone, it appears at around 1715, but actually this one appears around 1655. Excuse me. If it's ketone, it appears around 1715, but because of the hydrogen bonding, this carbonyl appears around 1650 or 1655, something like that. So about 60 reciprocal centimeter lower frequency is the place where the carbonyl appears. Amine group or amide group as well. This NH2 or NH bond appears around the 1555. Okay, so 1650 and 1550 is the location of these hydrogen bonded polyamide groups. Okay. Hydroxide as well. If you have hydrogen bonding, it's shifted to a lower frequency level. If it's a free hydroxyl, it appears around 3,400. But because of the hydrogen bonding, it moves a little bit, maybe 100 to 200 lower frequency level in this case as well. Anyway, you can detect this hydrogen bonding in your IR, and you can imagine how strong this hydrogen bonding is. Anyway, this hydrogen bonding affects your crystallinity. Okay, we will talk a little bit about the crystallinity in chapter 4, but the crystallinity is influenced strongly by this hydrogen bonding. Because of the chain regularity. Okay? If your chain is quite regular, yes, you can see this bonding. So the hydrogen bonding affects the crystallinity by contributing to the chain regularity. Okay? Chain becomes quite regular if you have a hydrogen bonding, okay, between the chain and chain. And this case will be exemplified the case of nylon or polyamide. Polyamide has the same as this one. Nylon is called the polyamide. The cellulose has a hydroxyl group. Okay, cellulose has a hydroxyl group, and the cellulose is a crystalline. Of course, it's a semi-crystalline. That's why we use cellulose in making fiber. Okay? That's why we are wearing your underwear, because of the crystalline cellulose materials. Cellulose has the para-para connected structure, whereas the starch has the cis structure. Okay? So that you have a little bit of a kinked structure in this starch, where the cellulose has a zigzag structure in the trans conformation. Okay? Excuse me, the configuration. Well, this is the polyimide cases. Okay? This ring is a benzene ring. So benzene ring is quite flat, as you can see. Okay? And benzene ring is not flexible. Okay? But if you have a carbon and carbon structure, if it's a single bond, it's rotatable. Okay? It's rotatable. But if it's a double bond, just like in the benzene ring, it's not rotatable. Okay? Benzene itself is quite flat, as I've just mentioned to you. And of course, if it's in the para position 1, the ring might be quite flat. Right? You can see, benzene ring. If it's composed of benzene ring, is quite flat, as you can see here in this case. So anyway, your regular structure, regularity, if it has a hydrogen bonding between the chain and chain, if you have another chain in here, if you have a hydrogen bonding, this bonding, extra bonding, such as a secondary bonding, will act as a cross-linker. So chain-chain interaction will be much more stronger and becomes much more flat and becomes much more packed structure in the space. So the polymer chain will become much more crystalline. Whereas the amorphous structure, okay, amorphous structure or the random structure, if it's random, such as the case of spiral group. Now this is the two different planes. Okay, this is one plane, and this is another plane, and it's not rotatable. If this is the case, if you put this polymer structure in the space, okay, it will not be much more packed, okay, just like the case of benzene rings. So that your density is much more, lower in this case than the previous cases. Okay? The chain-chain interaction is therefore very very important. Okay, along with the covalent bonding. Okay, dipole interaction is also important as well, as we have just seen. Now, the halogen atoms, such as chlorine and bromine, has a 3 unshared electron pair, as you can imagine. Those unshared electron pair will be used as a dipole-dipole interactions. So any component that contains the halogens, such as polyvinyl chloride or polyvinyl bromide, polyvinyl chloride is abbreviated as a PVC. Okay, if you have a PVC, if you look at the PVC structure, you have a vinyl group and you have a chlorines. Okay? Another, alternatively, you have a chlorine and so on. So chlorine will interact each other, okay? Because of the dipole-dipole interaction, such as the case of CN group. And therefore, you have a very strong material, okay, purely if it's in the PVC itself. PVC is therefore inherently very strong material. But if you add the precisizer between the chlorine and chlorine, then you reduce the dipole-dipole interaction between the chlorine and chlorine, in the case PVC. Therefore, you can make a flexible PVC as well. Okay? So PVC can be rigid PVC or flexible PVC, depending upon how you add and which you add. What kind of a precisizer you add into the PVC cases. Okay? If you talk about the PVC flooring, okay, flooring or wallpaper, well, it's a flexible. Or if you think about your wrap, okay, jajangmyeon wrap, if it's quite flexible. But if you think about your PVC pipe, okay, PVC pipe is quite rigid and strong. Okay? Flexible PVC has a lot of precisizer between the CL and CL group, whereas PVC pipe does not contain much precisizer. Okay? That's why the pipe can be fabricated as a rigid material. You have dispersive forces, just like what we have talked about, and it's the weakest interactive forces. Let me ask you some questions about the crystallinity then. Okay, so we have reviewed about the bonding, which is quite basic structure and it's quite simple. I think you all understand if you have already taken your general chemistry and the physical chemistry courses. The crystallinity is much more important than what we have just talked about. Polymer usually has a crystallinity, right? Crystallinity. Okay. And what's the crystallinity? Can anyone describe about the crystallinity? What's the crystals? What kind of crystals did you know? Well, can you calculate the crystallinity? Can anybody describe about the crystalline material? Do you know the crystalline material? I think I have elaborated a little bit in previous classes, but do you know the crystalline material? Salt, yes, salt crystals, yes. It's a crystal such as a sodium chloride. Ice crystals. Ice is a crystal. Well, what about the material that you're around you? The metal is a crystal. Is metal crystal? No. Well, if you see the TV screen, or if you have visited the POSCO, the foundry, you see the very hot, metal melts in the foundry, which is, it looks like a very, very hot metal melts. And if something melts, then means that your crystalline material will be melt. Okay. If your polymer will be melt means what? Melting temperature is defined as your temperature where your crystal melts. Your crystal becomes liquid phase from solid phase. So by definition, specific volume versus the temperature, if your material will have a discontinuity in your specific volume versus the temperature, temperature is defined as melting temperature, right? And in this phase, below the melting temperature, your phase is a solid phase, whereas above this melting temperature, your phase becomes a liquid phase. Okay, so phase change temperature is defined as a melting temperature. So what happened? Why the discontinuity between these phases in your material, such as metals? Actually, below this melting temperature, your material is in the form of crystals. If the crystal absorbs the heat, okay, absorbs the heat, and your crystal will become amorphous, or will become, irregular structure. From the irregular structure, will become irregular structure. Your volume will enormously increases. That's why it becomes a liquid phase. And in liquid phase, your entropy increases a lot, whereas in the solid phase, where your metal phase, crystalline phase, your entropy will become quite smaller. So you have explanation in terms of the thermodynamic phases of these melting phases. So this is the case for crystalline, 100% crystalline, or majority of material is in the crystalline phases. So metal is an example of your the crystalline material. Ceramic or inorganic material is a case of your crystalline cases. Okay, right? What about the polymer? Because this is the polymer classes. Polymer can have the crystals. In other words, not should have, but can have crystals. It can have crystals, or it cannot have crystals. So it's quite difficult. Okay, it's different from the metals and inorganic materials. Organic material, because we are talking about organic materials are sometimes flexible and sometimes quite rigid structure, depending upon your bonding forces. If you have secondary bonding forces such as hydrogen bonding, your material will become quite interacting each other. Therefore, you have a larger density. Your density will be quite increased. But if you have flexible chains, if you have your configuration, the conformation is a little different, or configuration is a little different, such as the case of starch and cellulose. Okay, cellulose is a crystalline, whereas the starch is not. Cellulose cannot be dissolved in any organic solvents because of the crystallinity. Your paper is composed of the cellulose. I don't think you can dissolve this cellulose in any organic solvents. However, starch, you have the same chemical structure but a little different configuration. The starch is soluble in water even. Okay, you can chew from your starch. From your rice, you can take your starch. It has the same chemical structure but different configuration, and your property is totally different. Okay? So that's a little bit about the crystallinity. So we have to think about in the case of polymer, we have some portion is crystals, crystalline portion, and maybe some portion is amorphous portion, flexible portion. That's why the polymer, in the case of polymer, we call semi-crystalline material. Most of the polymers are usually semi-crystalline. Semi means what? Half. It's not 50%, but it could be partially crystalline materials. Okay? Partially crystalline materials are mainly the case of the fibrous polymers. And we can also calculate the crystallinity. Okay? The important term is about the degree of crystallinity. How many percentages of your polymer is crystalline, and the rest of them are, of course, amorphous. Okay? So if you talk about the crystallinity might be 60%, then 40% is amorphous, of course, automatically. And this crystallinity affects a lot. from the chemical structure. So if you know the chemical structure, just like what we have seen in the bonding cases, if you know the chemical structure, you can imagine maybe this polymer might be crystalline or may not. Okay? So structure of your polymer is quite largely influencing your crystallinity. That's why in chapter 2, I think at the end of the chapter, I have elaborated a little bit about the nomenclature. So you should know about the chemical structure, okay? And you can name those, and you can also imagine the property of the polymers. Okay? So let's talk about the crystallinity again. Well, I don't think you have learned about the crystalline structure so far, but in your general chemistry course or your material science course, I believe, okay, you have learned about the types of crystals. Okay? I have elaborated only 6 representative crystalline structures here, where depending upon the length of your axis and the angle of your axis, we can elaborate maybe 6 types of crystalline structures here. Okay? For example, if you have 3 x, y, z, the axis have the same strength, and the angle is about 90 degrees or the same degree, we call this as isomeric. And if you have a little bit different perpendicular axis, we call this as a tetragonal, orthogonal, monoclinic, and stuff like that. Okay? And those structures are something like this, and we call this as sometimes a cubic structure, and so on. And in this class, in this the chapter, I do not want it to elaborate further about the crystalline structure of this polymer. The crystalline structure of the materials, because it's out of the scope of this the courses. What I would like to emphasize is that you need to know, you can calculate the crystallinity based on the information about the density of the materials. I emphasize a little bit more about the density, because density is related to your crystallinity. So in the next chapter, I have a structure here, which is a polyethylene. You have a CH2 structure, and it's carbon structure. Of course, it's a flexible. It could be rotatable. It's a rotatable structure if it's a single chain. Okay? If it doesn't have, if it has dipole-dipole interaction. Dipole-dipole interaction will make this polymer, which is the polyethylene cases, much stronger. Okay? If it doesn't have any dipole-dipole interaction, if it doesn't have a hydrogen bonding, then this structure, chain interaction is not strong, so that it could be, it could be in the shape of the random structures, and it becomes amorphous polymer. Let's say that we have this type of crystalline structures. Yeah, okay, assuming that we have this structure, which is isomeric, and some portions are amorphous, and some portions are the crystalline, and some portion might be 100% crystalline. In the later part of this course, I will show you how you can make the crystals. Okay, what type of crystals in the polymer cases, but at this time, I think I wanted to emphasize you that some polymer have crystals, and I wanted to show you how to calculate the degree of crystallinity. Okay? Degree of crystallinity or percent crystallinity. Percent crystallinity means that, for example, you have a 50% crystallinity, means, of course, half of your material is composed of crystalline structure, and another half is amorphous structure. And this percent crystallinity depends upon, of course, here, the density. density of your total. The S means solid, or the specific material of your unknown polymer, whereas A and C means amorphous, and C means the crystalline. So, for example, you have a polyethylene, okay? Low C is the case where you have 100% crystalline materials. So if you have a sample with 100% crystallinity of a polyethylene, okay, it measures your density, and this is what we call this low C. Okay, another case, low A, is 100% amorphous cases. Okay? If the polymer polyethylene is 100% amorphous, you make the sample and measure the density, and this is the value. Low S is the one that it is unknown. Okay? You make the polyethylene, which you do not know the percent crystallinity, but you can measure your density, because the density is defined as what? Okay? Mass divided by the volume, specific volume, right? Low is equal to m divided by v. If you know the mass, if you know the specific volume, then you can calculate the density, right? So by knowing the mass and volume, you can measure low S. So low S, low C, and low A are important parameters to calculate the crystallinity of your material. Okay? So this is, and you can derive this equation from the definition of a law as well. Because crystallinity is defined as the mass of a crystal. So how many the mass of your crystals in the total system divided by the total mass is defined as a percent crystallinity, and you can calculate this. Mass is defined as low times V, okay? Because low is defined as m divided by V, and you can add up this to here. Whereas subscript C, A, and S are crystalline portion, amorphous portion, and your specimen respectively, so that you can calculate this to you can convert this to this second equation, and the FC is defined as a volume fraction of your crystalline portion. Okay? So mass fraction will become a volume fraction in this case, and the volume fraction, from this definition, I think you can elaborate a little bit more. And using the volume fraction, you can come up with the final equation right in here. If you replace this FC in here. Okay? So if you replace this FC in here, I think you can come up with the final equation. In this final equation, if you know the density of your crystalline portion and amorphous portion, you measure the density of your specimen so that you can calculate the percent crystallinity. In the later part of this chapter, I have put the two techniques to measure your crystallinities. Okay? This is the direct method of measuring the crystallinity, but you indirectly you can measure your percent crystallinity by knowing the crystalline portion and amorphous portion, or your unknown sections of your crystals by using the instrument called DSC, differential scanning colorimeter, and the second technique might be the X-ray diffraction spectrums. So if you know the wide-angle X-rays and the DSC, thermal technique, we can calculate the percent crystallinity. Or we can measure the percent crystallinity in the later sections. Okay, so the crystals and amorphous portion are important, and I have I've shown you how to calculate the percent crystallinity by knowing the density. Density can be measured, of course. Okay? Density can be measured in the laboratory by knowing your specific volumes, using your Archimedes principle, right? Archimedes principle. You all know the Archimedes principle. So if you have a sample and put it in the liquid, and by knowing the volumes, you can and the mass, you can calculate the density. Okay? We have a densitometer in the laboratory, and I think later on, I will show you how you can measure the density. Or we have a floating method which means that in the density gradient column, okay, we have a big tube, big tank, and fill up with the liquids such as chloroforms or tetrachloromethane, which is a very high density material, and by floating the calibrated glass material or the metal material with the known density, and you can calibrate those density columns so that you know by knowing the position of the liquid in the column, you will be able to calculate the density calibration curves. And if you know those density gradients, then you put your sample of unknown density, and you will be able to calculate the density by those the density gradient columns. Okay? We do not have we used to have a density gradient column here, but I think rather than using density gradient column, recently I think we are using just a simple the balance to measure the densities. I think I will show you later on. Anyway, let's talk about how we can increase the crystallinity, okay, or decrease the crystallinity, depending upon your conditions. Okay? Well, the crystallization is actually influenced by the packing. Okay, your packing. I think I showed you how the chemical structure or your structure is very important for the packings. Okay? Packing influences your density, okay, and compactness. Structure. Your structure is very important. Okay, if your structure is flat and linear, there is a lot of chances to become your high density. If your chain is a little kinked, so that it's not regular, if it's irregular, then there is a lot of chances that your density is quite lower. Okay? So packing and density and compactness always be influenced by the regularity, of course, stereo regularity. Okay? And that influences your degree of crystallinity, of course. And the packing always was influenced by the secondary bonding forces. If you have a hydrogen bonding, if you have a dipole-dipole interaction, then there's a lot of chances that your chains will become packed, will become regular. Okay, so it becomes much more crystalline. Now I have drawn just a picture here, where you have a polymer film. Some portion might be crystalline, and which is represented as a circle, And uncircled portion, which is background portion, is amorphous. So crystals are embedded in amorphous portion. Let's imagine that states. For example, if you have your polypropylene film, wrapping film, or I think packaging film, or in your, perhaps somebody is smoking, your wrapping film or packaging film with a cigarette is composed of polypropylene. Let's say that you have a polypropylene film with a semi-crystalline structure. So you have some crystalline portion and amorphous portions. And we increase the temperature, okay? If you increase the temperature, then your crystalline portion will be melt, okay? Will be melt. So at the melting temperature, your phase, which is in the solid phase, will become liquid phase. Because of the discontinuity, it expands a lot. That means that your crystalline portion will absorb a lot of heat, so it expands. Your specific volume increases, and all the portion will become amorphous. And this is the case of melt or molten state. Melt means MELT. And melt means that your crystals are all gone, becomes a liquid phase. And at that liquid phase, your chain, you still have a chain, of course. Okay, polymer chain will have a lot of flexibility, just like water. Okay, a lot of flexibility in this case. This is the solid phase. This is the liquid phase. At this liquid phase, you wanted to cool down your molten state or melted state. Okay, you cool down to become a to become solid phase. Okay, solid phase. But but if you apply the stress, okay, like orientation, then your polymer chain will start to have orientation, so that it just like to have aligned in one direction or two directions, depending upon your stress directions. So if you stress a little bit, your polymer chain will be aligned, right? Aligned, just like in this case. So you have more orientation in here. So we have two cases where we have original solid phase and oriented solid phases. Crystallinity is not the same. Although we start from the semi-crystalline material, you have a semi-crystalline material again, but depending upon the conditions, your crystallinity is quite different. But you do not change your polymer structure, but crystallinity changes depending upon your conditions. So processing condition, okay, processing condition influences your crystallinity of a final product. And of course, the history, this is the same chemical structure between the two samples, okay, but history is different. History is different. History will make you different materials. You have you have your own history, and I have my own history, and I'm not the same person right now here than 10 years ago, right? I am the same person, but I'm not the same person, okay, now and 10 years ago, okay? But that's, you see what I'm saying, okay? You have the same polypropylene, but because of the different history, you have a different crystallinity, you have a different property. Okay? Chemically the same, but physically different, depending upon your conditions of your history. Now, in making the stretching, okay, stretching is something like this. Okay, this is what we call uniaxial stretching. You stretch in one direction. Okay, it's called uniaxial stretching. if biaxial stretching, by the way, biaxial stretching is the one that you of course stretch in one direction, and at the same time you stretch in the y-axis as well. It's called the biaxial stretching. In industry, they use a lot of these biaxial stretching cases. Okay? If you stretch in one direction, your length, the width might be decreasing a little bit, like here. But in the biaxial stretching, your y-axis will, in fact, become larger. So stretching is in both cases, x-axis and y-axis. You have much more the orientation, and you induce a lot of crystallinity by biaxial stretching. And I believe that your packaging film for your polypropylene, they use a lot of biaxial stretching in the industry. So degree of crystallinity or percent crystallinity depends upon the processing conditions. Processing conditions such as the stretching, and of course cooling rate as well. Cooling rate. Okay? For example, if you go back, now once we make a melt, okay, we make a melt, and I just mentioned to you that the stretching is quite important. However, once you melt, melt means that you put your solid film in your oven, for example, okay, up to above the melting temperature, which is the case of maybe 250 degrees C. Okay? If you put your film into your oven, heat it up, and your film will be melt if you have a crystalline portion. Once it's melt, okay, in the oven, you have two options. One option is that you just open the door and put your melt on top of glass plate film, put it into room temperature. Okay? Or second option is that you just let it leave there inside of your oven, and you just turn off the oven. Okay? First case is the case where your temperature of your film, if you are the film, okay, think about it. If you are the film, then your film, you are at 250 degrees C, and rapidly your temperature is becoming 25 degrees C within perhaps 30 seconds. Okay, so cooling rate is quite rapid in the case of first example. Second case is that you just leave your 250 degrees C in the oven and just to turn it down. So the cooling rate is quite slow, in fact, right? Quite slow. You just let it cool down into your environment. So first case is the slow cooling case, where the second case is the fast cooling case, whereas the second case is the slow cooling case. Okay, fast cooling case and slow cooling case will make your crystal different shape. Okay? Can you imagine the fast cooling and the slow cooling case? What's the difference? What makes the crystals different? Anyway, the cooling, well, I think I have elaborated here. So when you think about your two cases, your crystals, when you cool down, you start to make the crystals, right? Because it's in the reverse direction. It's in the reverse direction. You start to form the crystals. Start to form the crystals, but you start to form the crystals. If it's in the start to form the small crystals. Small crystals are present if it's very rapid. Okay? But if it's very slow, then there is a time. Rapid and slow means time scales, right? If it's very slow, then there is a chance to grow your crystals. There is a time to coalescence, aggregate your crystals together. So your crystal of your final polymer will become large in the case of slow cooling cases. If it's quite rapid, you do not have a time. If it's pali-pali, if it's very, very rapid, you do not have a time to get together. Okay? So this case is the rapid cooling case, where this case is the slow cooling case. Okay? So the cooling rate will make you different crystalline structure. I don't know which is much stronger or not, but anyway, the crystals are quite different. Okay? Let's go back to the. So cooling rate influences your, crystallinity and crystalline structure, as you have already seen. And also the second, important aspect of the crystallization condition is that your chemical groups or chain configuration, regularity, irregularity, influences your crystallinity, of course. Okay? If you have a smaller side chain, if you have a linear chain, then your crystallinity will become much more stronger or higher. Whereas if you have a bigger side chain, longer side chain, if it's not linear, okay, if it's not linear, your packing density is smaller, so your crystals are quite less. Okay, so there's always several aspects affecting your degree of crystallinity. Conditions, cooling rate, stretching, those conditions are influencing your crystallinity. And chemical structure and the configuration always influences your percent crystallinity. If it's a cross-linked structure, it acts as influencing the lower density cases, so the crystals are quite less. Now this picture is similar to this one, right? Similar to this one, but not the same. And what's the difference between this picture and this one? Did you find any difference? I want you to speak. Okay, any difference between these two? Yes, TG. TG is right here. Okay. TG is right here, whereas in this picture, you don't have any TG. So this example is the case where the metals or the inorganic, like ceramics, those two cases are almost 100% crystalline structure. Well, in the case of polymer, we have a TG. We have a glass transition temperature. So TG is defined as a glass transition temperature. And in fact, the slope from low temperature to TG and TG to TM is different. Okay, so you have a little kinked structure, kinked slope at glass transition temperatures. In other words, as you increase the temperature, your specific volume increases. And the rate of increase or degree of increase is changing at glass transition temperature. So above glass transition temperature, your specific volume changes a lot compared to below TG. Okay, so there is something happening. In this region, and this region is again the solid phase. And above this melting temperature, this is the liquid phase. Okay, so the melting temperature, below melting and above melting is the same. You can describe this as a same principle, just like in the case of metals and the inorganic materials. But emphasis should be given to the glass transition temperature in the case of polymer. Okay, so let's think about these cases. Well, actually, if you increase the temperature because of thermal motion, your chain, in any case, your chain will be moving, right? If you heat it up, if this room is heated up, I think you start to be inconvenient. I mean, uncomfortable. So you start to move. Okay? If it's very comfortable, then I think you can concentrate on my talk. But if this room is quite hot, then you cannot concentrate on. So you have to start to move. Somebody will go to the restroom and so on. Right? Anyway, if you think about your polymer chain, for example, polypropylene, you have a side chain, okay? And you have backbones. At low temperature, if you think about your polymer chain, if you think about my body or your body, if you increase the temperature, a little low temperature, your body itself, it will not be moving, but perhaps your finger might be moving. Okay, a low temperature, your finger might be moving, but you need some. Well, at a frozen temperature, if the temperature is frozen, you occupy some space. Okay, and the volume that I'm occupying is called the specific volume. Right? The specific volume. So I occupy the volume in the space. But as you increase the temperature, I move my finger. Okay, so I need some unoccupied volume, which is extruded volume, okay, or free volume. So I need this amount of the volumes. So my specific volume increases as the temperature increases, right? But if you increase further, then my arm should move along with my finger. So my specific volume increases, of course, a lot too. Okay? If specific volume increases in the case of below glass transition temperature, there are some, of course, the specific volume increases as you increase the temperature, but the increase of your free volume is quite relative. So you have a same slope. But if I'm moving my body, okay, along with my arms, my specific volume, of course, is quite different. My slope of my increase your space volume above glass transition temperature up to about melting temperature is different, right? Because I need some more spaces as well. So below glass transition temperature, I would say the side chain of your polymer is moving, okay? And above glass transition temperature, perhaps your main body might be moving. Okay? So the slope is quite different. All those phase is a solid phase, but the movement of your side chain versus your main chain makes the change in your specific volumes below and above the glass transition temperatures. Okay, but that's at the lower, the solid phase. But above the melting temperature, or if you reach the melting temperature, okay, it will become random. Okay, you have of course you have a lot of motions because of the expansion of your or the melt of your crystals. Anyway, below the melting temperature, you have two different slopes. So the change, so there are some diffraction points where the critical temperature, where the phase changes. Phase in the solid phase, below the glass engine temperature, we call this as a glass state. Glass state. And this is the rubbery state. So the TG is defined as the temperature where your state becomes a glassy to rubbery state. Okay? Glassy to rubbery transition temperature is called a TG. So every polymer should have glass transition temperature. Every polymer should have TG, but may not have TM. Okay? Every polymer should have TG, but TM may not be present in polymer. TM is a melting temperature due to the presence of crystals. Okay? The polymer can become crystalline polymer, or 100% amorphous polymer. But amorphous or crystalline polymer should have, both of them, should have TG. So TG is the different property compared with the metals and ceramics. Okay? So if you have an interview with the professor or at your advanced graduate school, or if you interview with the people at the company to be hired, they will ask you whether you took a polymer chemistry course. If you take a polymer chemistry course, they will always ask you, what's the definition of TG? Okay, and how is it different from metals and ceramics? And that's the very typical question about the polymer chemistry and polymers. Okay? So TG is very important in polymer. I think I should continue on the Friday because of time.